fascinated by the problem of earthquakes. They're interesting. They combine condensed matter physics, they combine mathematical physics, they combine geological observations, but they also combine what we see here. We see an image of the world. We all know that there are a lot of people on Earth, and this is a particular part of the world where a lot of people live. It's Eastern Asia. At night, you can see everything lit up. And that drives a lot of us. We want to not just understand what's going on. We want to not just say intelligent things about it, but we want to somehow make a contribution to making the world safer for people who live in harm's way, specifically the harm of earthquakes. And so for a long time, I've thought about this problem, and I've really focused on it through the lens of what we can observe largely when earthquakes aren't happening. And here's a couple of figures that show how we learn about the world when big earthquakes at least aren't happening. The primary data set that we use for this is geodetic data. Geodetic data is common to all of us nowadays. We all walk around with phones in our hands and we can see which side of the street we're on. But there's kind of industrial scale geodetic data too. The top panel here shows an example of a GPS time series from Japan. Japan has an incredible geodetic network. It's been running in part since 1996. And the upper panel here shows a time series that runs for more than 10 years, almost 20 years. And the first part of it, the kind of bluish to purplish part, that shows what's going on before a large earthquake. At day roughly 5,400 or so, you can of course see a jump in this time series. This will surprise nobody to hear that this is the Great Tohoku earthquake that happens on that day. On that day, this GPS station, its east component of displacement moves about 2 meters. And then after that, we have this kind of orangish yellowish part, which is kind of an interesting post-seismic part. Now, when you look at these data, most of the work that's done in earthquake science is done about what happens when there's a jump in the data. What happens on that day when the big earthquake occurs? A lot of work also is focused on what happens after that, what happens in what's commonly called the post-seismic regime. What I spend most of my time working on is what happens before large earthquakes occur. This seemingly boring bluish purplish part, this part of what's sometimes called the interseismic part of the earthquake cycle. And you've seen pictures like this before. The one below shows what the geodetic network in Japan was doing for a 4-year period, roughly in the early 2000s, when Japan was devoid of many large earthquakes. So what's done here is we take the interseismic velocities at each station and we plot them up. And you can see a lot of things that you're familiar with. You can see that there is a gradient in deformation across the Japanese islands. This reflects largely a component of shortening associated with the process of interseismic strain accumulation. But you can see that there's lots of complicated changes too. Down south in Kyushu, we actually see trenchward motion, whereas in Shikoku, Honshu, and Hokkaido, we see motion away from the trench. So we spend a lot of time not just looking at these data, but we spend a lot of time building mechanical models of these data. And those of you who have heard a talk from me over the past 20 years have heard a lot about this. The primary way we do this is we try to take a velocity field and we try to decompose it into 2 parts. One part associated with plate tectonics, that is the rotation of shells on a sphere, and another part that's associated with earthquake cycle processes. The cartoon on the left here shows like an idealization where we have kind of 3 blocks or plates meeting each other. They're hexagon shaped here. In nature, that diverges a little bit. And at the interfaces between those blocks or plates, that's where we have faults. The colors on this image here represent kind of a cartoon representation of where faults might be stuck together. And we've built a lot of mathematical machinery, more specifically a lot of computational machinery, to do this at very large scale, to take geodetic data and to take models of the Earth that have blocks and geometrically complicated faults, and then decompose velocity fields into the parts that are associated with the earthquake cycle and parts that are associated with plate tectonics. When we do that, one of the things that we get out of it starts to be interesting, and that's shown on the on the right here. What we see on the right is a map of the greater Japanese islands region. Up to the north is Hokkaido, and then to the south is kind of the upper 2/3 of Honshu. Subduction zone is kind of hanging out there, and the parts shaded in red are estimates of what parts of the subduction zone were coupled, strongly coupled together, that is not creeping, prior to the Great Japan Earthquake of 2011. And when you look at this map, you see that a lot of the subduction zone, that is the parts that are colored red, were fairly stuck together prior to the earthquake. The black lines here, these show an estimate of what happened during the earthquake, specifically where slip occurred. You can see that there was a lot of trenchward slip, which caused the tsunami that caused so much devastation. But there was also a down dip slip that extended to a depth of as much as, say, 40 kilometers or so. Now, the thing that got people interested here was that there was some spatial correlation here between where interseismic coupling was occurring and where coseismic slip occurred. And this is potentially interesting because it offers the prospect of us saying, if we can identify regions where coseismic slip, if we can identify regions where coupling is happening, we may be able to identify regions that will host future large earthquakes. That seems like something that we should probably spend our time on. When we look at this map here, one of the things we see is that the Sendai region here is not the only locus of strong coupling in the greater Japanese islands. We see strong coupling off the coast of Hokkaido, which is far greater than the amount of release during the Tokachi-oki earthquake in 2003. And we see that the Sagami and Nankai subduction zones are pretty coupled as well. So this is kind of neat that I show you an example where I have one possible correlation between coupling and where an earthquake occurred. I don't know how many people here have had a statistics class, but I'm pretty sure a sample size of 1 is not something that's considered really, really good. And so we kind of have two options here. One, we can wait. We can wait hundreds or thousands of years and just wait until there are more large earthquakes in Japan and see if they correlate. The other thing we can do is we can start to think larger. We cannot restrict ourselves just to one study area, one regional study area, but we can try to look globally. And this is what we've done in a series of papers with Shannon Graham. Here, what we did was instead of looking just at Japan, we tried to look at, to some approximation, the entire globe. The figure on the left-hand side here shows a representation of the global fault system, incomplete as it may be. And every part in red here, these are subduction zones, or in the case of the Himalaya, shallowly dipping continental thrust fault, on which we estimate spatially variable coupling. This is a very large scale model. It's nearly 20,000 GPS velocities, 16 major subduction zones. And one of the things we can do with this is use the exact same type of logic we did with the Japan case. So we come up with maps of where things are coupled, and then we can say, all right, if things are coupled here, let's imagine for a second, not knowing that this is true, but let's assert that we could estimate the sizes of future earthquakes based on the idea that some coupling threshold, some coupling level defines a kinematic extent of an earthquake. And if you do that, you can develop global earthquake scenarios for large earthquakes. And that's what's shown on the right here. We break this down into each subduction zone, and you can see along kind of the x-axis, there's a recurrence interval for events of a certain size. And then for each of these subduction zones, based on the current set of geodetic data that we have, what is a set of scenario earthquakes that would kind of fill up those coupling regions? What would kind of balance the budget out? And this is what you get. You get depending on how you do the calculation, you get somewhere between 4 to 12 magnitude greater than 9 events with recurrence times less than 2,000 years, and almost all of them with recurrence times around 500 years. One of these that's included in this model, which is not a prediction, it's a retrodiction in this case because this study is much more recent, is the Japan earthquake that's already occurred. So that sounds a little bit interesting, right? We can say, all right, we can, based on geodetic data that we have today, we can try to estimate where future large earthquakes might happen. But that leaves us wanting too. Even if we like that logic, the best we're doing here is we're saying, okay, maybe we can say something about where and how big large earthquakes might occur. And we're talking very large, magnitude 9s here. But there are lots of other earthquakes that can occur too. And we'd like to say something about those. That would be useful, not only in terms of hazard, but that would be useful because it would provide us with a huge amount of data to validate models against. So how do we do that? Well, there have been people working on things like this for a long time. And one of the core ideas is not to just use this kind of metric that we argue for, that earthquakes tend to occur in coupled regions, but instead to build physics-based models of earthquake sequences. This has become a very interesting thing that people have done. And people started this really in the 1980s with some really lovely work on the anti-plane strain 2D strike slip case. And that work is still continuing in many ways. As we think about this doing this kind of in the real world for real fault systems, it gets pretty complicated. And there are many complications from variations in material properties to nonlinear rheologies. But I'll suggest that perhaps the strongest nonlinearity is the nonlinearity of geometry. Fault systems are incredibly geometrically complicated. They branch, they anastomose, they are fractal to some extent. They're just these incredibly geometrically complicated structures. And so honoring that geometry and trying to understand it is something that I think deserves a lot of attention. So with that in mind, there are kind of two main ways to go about thinking about this. More than two. But one way to start building physics-based models is to use finite elements or finite difference. That's really good too. Finite elements a little better for complicated geometry. So with finite elements, we take some volume like we see here, and we have two faults in it. Those are the two kind of dotted lines in the middle here. We discretize the whole thing, and then we solve the equations of motion along with something like rate state friction on the faults to generate earthquake sequence models. This is a well-established technique. It gives you large sparse matrices, which are very nice for modern computing architectures. It just has one small problem, and that is it requires volumetric meshing. And volumetric meshing for complicated geometries is challenging. Hughes, Hughes of all the finite element textbook fame, has this great quote that 80% of overall analysis time is devoted to mesh generation. And that's if you can successfully mesh the volume at all. And so that's a fundamentally hard problem. And I don't know the extent to which we're going to be able to mesh all the geometries that we want to mesh. There's another way to think about this that avoids the meshing problem, and that's instead of using something like finite elements, you can use boundary elements. Boundary elements produce large dense matrices, and instead of kind of having these local to local element interactions, they have all element to all element interactions. So every single part of the fault interacts with every single part of the boundary. Now, what's great about these is that there is no volume meshing at all. And so that you can, in theory, do a lot of really wonderful things with them. How does the math work for these? So you've probably seen this before if you've ever looked at a book on boundary elements, but the core idea is that there's a set of displacements that we call U here, and they can be calculated from an integration over all of the boundaries that you have here. The displacements from the boundaries that set boundary conditions, as well as displacements from fault slip. You can do the exact same thing with the stresses as well. Stress is written as a stress vector here rather than a tensor, just to make it look nice in linear algebra sense. The cartoon down below here, this shows the interaction between two elements. The stress on one element interacts with the stress on another, and the stress on one element also critically interacts with itself. This is called the near field stress calculation, or more specifically, the coincident stress calculation. And the far field stress calculation, the stress from one element acting on another that's far away from it, that is very, very accurate in boundary elements. The coincident stress calculation, that is the stress of one element onto itself, is much more complicated. And what I'm going to do now is kind of take you through a journey of how we think about calculating that, because it's something that's critical to calculating accurately if we want to do something like model stresses on a fault. And we'll see that it gets a little difficult. So let me start by showing you a problem. The problem we're looking at here is a classic problem in continuum mechanics. It's a classic benchmark. It's called a compression test, or sometimes called the Brazil test. The core idea is that you have some circle here, and this circular disk in 2D is compressed by forces that are applied just at the edges. And you can do it over some arc of the body as well. You can do this in the laboratory, I guess, and you can do this analytically. There's an analytic solution for it. So the top panel here, the top row, shows the stresses in 2D for the case with the analytic solution. And you can see they're localized because we just have little forcing stresses on the edges. The middle row here shows the solution with a very high resolution boundary element code. And if you look at them, they look remarkably similar. At first, this seems like a really good thing. This seems like, hey, we can do this well. But if you look at the difference between the two, if you look at the residuals, you can see that almost everywhere along the boundaries, you can see that there are errors. You can see those little white lines popping up, and they're not localized just to where the forces are applied at the positive and negative x end of the circle or the disk, but those errors are showing up everywhere. And it turns out these errors are pervasive, and they are extraordinarily hard to avoid using classical boundary element formulations. And they often give rise to critically wrong solutions. So let me make that case by doing one of the most boring things on earth, which is showing you some error analysis. Here's a figure that shows some of that. So one of the critical things to think about is most of the time when people do boundary element work, boundary elements are done by assuming that slip or displacement is constant over over a single boundary element. And then you discretize things so that you build up a gradient in slip as the summation of slip from a bunch of constant elements. Now, this figure, while initially complicated, conveys a lot of information about how well you can do with that approach. Here, what we're doing is we're looking at how well we can fit an analytic solution for a specific problem. I'm not going to detail what problem it is, where we're looking at the solution not at the boundary where there's definitely going to be problems, but slightly off the boundary so that we have some hope of resolving things a little bit. And the top panel, the top row here, shows the solution for 3 different cases. One, the dashed black line, that shows the analytic solution. That's a true analytic solution for this case. That's mathematically accurate. And then we show 3 boundary element solutions. The ones that are important here are the ones that are shown in the light blue or the cyan, and the one that's shown in the red. The one that's shown in the light blue or the cyan, that's what you get if you use a fairly high resolution constant slip boundary element approach. The ones that are shown in the red are what you get if you use what's called a higher order method, using instead of constant slip elements, using quadratic elements, which are a proposed fix for this. And what you can see is shown really clearly at the center top figure in particular. And the center top figure, we're looking at the YY component of stress here. And what we can see is the dashed black line has this kind of 1 minimum in the middle of it here, and that's the true solution. And all of the other solutions, whether they're constant slip elements or quadratic elements, they have singularities everywhere. Well, not everywhere, in many places. They're going up and down, and the error changes sign, not arbitrarily, but changes sign in different ways around the true solution. The panels below show the same thing, only they're showing the residual magnitudes. The important thing here is as you go down the center column here, you can see that the errors here, in terms of their magnitudes, are on the order of 10,000 to a million times. In all of these cases, the stress error near false is not only large, but the sign can be arbitrarily different from the true sign. And this is a situation that we probably don't want to rely on if we're trying to do this. Understanding this is not a discovery. It is well known in the numerics world. There's been some recent work that's been very exciting on this by Andreas Klockner. He proposed a method called quadrature by expansion back in 2013, which kind of starts to address this. And it does so by saying, we not only want a solution that satisfies the equations of motion, but we also want a solution that satisfies the equations of continuity everywhere. And so quadrature by expansion is one proposed method to do this. It's a brilliant method. It's not at the stage where we can kind of just roll it out readily for these problems yet. It's still kind of a numerics research type of thing. So a lot more work is needed there. Let me show you one other thing that is a little less than fun with boundary elements. Here, I'm showing stresses from a boundary element calculation done for a really simple problem. Imagine you have a fault which just has some gradient and slip on it. It has some, this is a plane strain problem. It slips, let's say, 10 millimeters per year here and 1 millimeter per year here. They're separated by some set of units here, which is 10 kilometers or something like that. And there's just a smooth gradient and slip here. The top row shows the stresses that you would get if you used constant slip elements and discretized the entire thing into something that had steps in it. I don't know how many steps I use here. It looks like there are 6 or so or something like that. What you see there is this kind of beautiful butterfly pattern in the stresses. This is very typical of what we see in a lot of publications where we see the kind of these butterfly patterns, stress changes type of things. Those butterfly patterns, those emerge because of the displacement discontinuity at the edges of each of the constant slip boundary elements. That is a discretization and parameterization error. If you use linear elements in this case, which is a degenerate version of the quadratic ones, what you can get is something like what's shown in the middle row here, where you get beautifully smooth stress calculations all the way through. That's fine, and that's a little interesting, but I also just told you that even using quadratic elements doesn't solve the accuracy problem in general. Here, I want to go back and address the constant slip boundary element case by having us look at the stresses on the bottom. And here, what we see is that on the bottom left, we see the XX stresses. In the bottom center, we see the YY stresses. And on the bottom right, we see the off-diagonal stresses. And for the off-diagonal and the sigma YY, you can match the analytic solution very, very well. But if you want to get the sigma XX stresses in this case, constant slip boundary elements will always, always, always give you a self-interaction of 0 for the XX case. And here we know we have some linear gradation in this problem as defined, and you can never recover the sigma XX from that. So constant slip boundary elements cannot recover the full stress tensor, even in very simple cases. Going to quadratic slip boundary elements is still not very, very accurate at all. So I share this because I think the most promising method that we have for handling complex geometries in fault systems is deeply challenged in terms of being accurate enough to do what we want it to do. This represents not the happiest state of affairs, but it also represents a lot of hard-earned numerics knowledge, and the numerics literature is very sophisticated on the challenges faced by methods like this. Now, having said that, what do we do? What do we do if we can't, as of today, build the numerical models that we want to? Well, we might want to think about this problem in a slightly different way. And there's an editorial that I read years ago that helped me start thinking this way. An editorial by Frank Wilczek. It appeared in Physics Today, probably 2004, so 18 years ago. And it's a really provocative it's not an editorial, it's more of a commentary. It's a really provocative article. Whence the force of F equals ma? Part 1, Culture Shock. In this set of 3 articles in Physics Today, Frank Wilczek, who's a physicist, he won a Nobel a few years ago, he makes the argument that force might be something that we want to consider a little differently. And I'll use force and stress interchangeably here. He introduces the idea that when he was younger and he took classes about physics, he had trouble understanding the notion of force. And he kind of runs with this a little bit. He gets to this, I'll read from this paragraph here. The paradox deepens when we consider force from the perspective of modern physics. In fact, the concept of force is conspicuously absent from our most advanced formulation of the basic laws. It doesn't appear in Schrödinger's equation, or in any reasonable formulation of quantum field theory, or in the foundations of general relativity. Astute observers commented on this trend to eliminate force even before the emergence of relativity and quantum mechanics. Astute observers, including Bertrand Russell, who has a famous piece called On the Abolition of Force, published in 1924, I think. The second part of this, Wilczek carries on. He sees force as essentially a problem-solving tool that is introduced from time to time, and he calls it a culture. The concept of force, as we have seen, defines a culture. In previous columns in this series, I've indicated how F equals ma acquires meaning through interpretation, that is, additional assumptions about F. This body of interpretation is a sort of folklore. It contains both approximations that we can derive under appropriate conditions from modern foundations, and also rough generalizations such as the laws of friction and elastic behavior abstracted from experience. I was thrilled to read this in so much as he was clearly thinking about earthquakes at the end of this, and it's great to have a Nobel laureate talking about earthquakes. As strange as this may seem at first, it actually connects to other things in physics, and it's prompted me to think about how we can try and make progress even when we don't have access to numerical methods for solving the equations of motion the way we want to. And lots of physics does this. In fact, there's a whole field that thinks about things this way, and that's the field of thermodynamics. Here I'm going to read a quote from Sadi Carnot from the one book, the one thing that that we know Carnot published in his lifetime. He only lived to 36. He died of cholera at a very young age. His work was virtually ignored. It only came to prominence when Clapeyron found it about a decade later. But now Carnot is considered his work is considered kind of the foundation of thermodynamics. And here's a rationale for thinking thermodynamically that Carnot gives in his paper. The principle of production of motion by heat, is thinking about steam engines here, must be considered independently of any mechanism or particular agent. It is necessary to establish principles applicable not only to steam engines, but to all imaginable heat engines. And what's cool about this is Carnot is thinking about this and saying, what can we say that is true essentially for anything that goes on inside of that engine? What are the general principles that might govern every single engine? Which I think is a powerful way of thinking. And most importantly, it's a very humble way of thinking because it allows us a way forward when we don't know all the details or we can't do all the details the way we want to. And so what I'll offer here is a riff on the quote from Carnot, where all I've done here is I've taken the parts that were outlined in red and I've replaced them I've taken the kind of heat-oriented things and I've replaced them with terms proximal to the earthquake cycle. So this is the quote, just injecting a few different words. Here, the principle of the production of fault slip must be considered independently of any mechanism or particular agent. It is necessary to establish principles applicable not only to linear elasticity and rate state friction, but to all imaginable rheologies. I think that's an interesting way to consider thinking about problems. What can we say about a system that's probably true for all sets of mechanics, not just the ones that we may be studying at a particular time? And so This offers us kind of a way forward towards a type of what might be considered almost a type of radical empiricism at first. And I'm going to start talking about how we can build earthquake cycle models based on this idea, based on the idea that we want to be able to say things that are generally true with the macroscopic or mesoscopic observations that we have, even in the absence of our ability to solve things in the way we want at the scale we want. So to do that, we're going to start kind of counting up, developing kind of a catalog of things we want out of an earthquake cycle model. And I've listed about 9 properties that I think are things we'd want in an earthquake cycle model. This is by no means comprehensive. It's just a set of 9 things that seem relevant in terms of observations. The first thing we might want relates back to the beginning of the talk. We want an earthquake cycle model that is consistent with earthquake cycle loading. We want this idea that earthquakes tend to occur, not always, tend to, but not always occur in regions that are coupled to some extent. We want them driven at rates that are related to how fast plates are moving and things like that. We also want earthquakes to occur more frequently after large main shocks. We want some Omori style behavior. At the same time, while we want this increase in the frequency of events following large earthquakes, one of the other things we seem to observe are delays between large earthquakes. We don't have a lot of scenarios where one magnitude 9 happens somewhere, and then we have a series of 10 other magnitude 9s happening within a day or a week everywhere else on Earth. That's just not something that we've yet observed. It doesn't mean it couldn't happen, but it's not something that we think we've yet observed. Rather, we see things like we see on the bottom figure here. Bottom figure, it shows surface slip from a series of earthquakes along the North Anatolian Fault over the last 80 years or so. And they're organized chronologically, and they also happen to be organized roughly east to west. So the most recent of these was the Izmit earthquake in 1999. That's shown kind of as the top line here. And then prior to that, one prior to that was 1967, so approximately 30 years difference. 1957, 10 years difference. 44, 13 years. 43, 1 year. 42, 1 year. 39, 2 years. So between these large earthquakes, we tend to see these kind of delays in occurrence. There are paleoseismic data that constrain this as well, from the Cascadia subduction zone to the Alpine Fault, which appears to have quasi-periodic events. I'm thinking of the Berryman paper in particular here. And so these are 4 things we'd like out of an earthquake cycle model. The top 2 items here have something to do with where earthquakes occur and how they're loaded. The bottom 2 have something to do with time. Well, there's more things that we want here too. We'd like the frequency distribution to be consistent with something observable. It could be the Gutenberg-Richter frequency distribution or some other one. We'd like the size of earthquakes to have something to do with their magnitudes. People have spent done a lot of really interesting work trying to develop scaling relationships between the average slip area in large earthquakes and small earthquakes and their magnitudes. We'd also like small earthquakes and large earthquakes to potentially be a little different from one another. We'd like small earthquakes to rupture roughly circularly, consistent with crack theory. We start as kind of little circular things and they kind of grow from there. The figure here is showing a numerical example from Camilla Catania's work with Paul Siegel. At larger scales, we want earthquakes to kind of be limited in their rupture extent by the geometry that's available to them, whether that's the interaction with the surface, whether that's a bend in a fault zone, whether that's some change in rheology that's temperature or pressure modulated with depth. We want ruptures to be limited by the extent to which they have fault geometry available to them. And the other thing we want is we don't want ruptures to be homogeneous. We want them to have heterogeneous fault slip. Here's an example from the Ridgecrest earthquake, which happened just a few years ago, of one realization of what some people have argued fault slip looks like. And you can see here the darker regions indicate greater magnitude fault slip, and it's highly heterogeneous here. We are limited in our ability, both by the data and resolution of the inverse problem to see these things, but we have decent reasons to think that there might be deep roughness in earthquake ruptures. So what I'm going to do now is I'm going to take these 9 items and show you how they can be combined into a statistical earthquake sequence generator. And I'm going to start not with item 1, but with these items here, generating spatially rough slip. It turns out that there are really wonderful ways to do this. Here's an example of a synthetic slip distribution from magnitude 9 earthquake on the Nankai subduction zone. So this is, it's shown in 2D here, but this is a 3D subduction zone. The northern part is the deeper part here. The slip distribution was realized using the technique that Levesque wrote about in 2016 and Melgar followed up on in the same year. The core idea is incredibly simple. It says what we're going to do to generate a slip distribution is we discretize the fault surface in some way. In this case, we discretize it in triangles so that it's nice and gapless. And then what we do is we come up with some approximate area that the earthquake should be. That's easy enough to do using scaling relationships. And we then want to generate rough slip on it. Well, how do we do that? Well, we just generate, all we have to do in theory is generate a set of eigenmodes, and then we can just weight them however we want to generate slip. The key insight that Levesque brought in his paper, which was truly important, was Levesque recognized that you could use something called the Carhouni-Love theorem, which is very straightforward. It looks fancy on paper, but all it says is this. If you use a Gaussian distance correlation matrix, you can get a guarantee of orthogonality when you take the eigendecomposition of that matrix. So you can do that. The top set of panels here show a couple of eigenmodes from this, what happens after you take the SVD of the Gaussian distance correlation matrix. And you can see there's an eigenmode where you have uniform slip, one where slip is partitioned roughly east to west, up dip, down dip, and then all of these higher order modes. For this large earthquake, I actually do the sum from almost 20,000 modes, and you can see that the peak slip reaches up to about 32 meters here, and it has this kind of really beautiful looking spatial decay to it, but it's not monotonic. So generating large earthquake slip is a straightforward thing to do, and it's thanks to the core idea from Levesque. Now that's a good start. This tells us how to generate an earthquake. We can do this for any magnitude earthquake. What else do we need to do? Well, one of the things we need to do is we need to think about how earthquakes change the state of the fault itself. And typically we'd run to stress to do this. Stress would be where we go to figure out, how has this fault changed as a result of an earthquake? But we can, following kind of the thermodynamics analog, we can generalize away from that a little bit, and we can track something else, something that doesn't require us to know or calculate stress. We can calculate something that's purely kinematic in nature, and that's the geometric moment. The geometric moment of anything, whether it's related to earthquakes or not, is just the area of some element multiplied by the motion or slip of that element. For earthquakes, that is the slip on some fault patch multiplied by the area of a fault patch. A lot of us are more familiar with the classic moment, which is the same quantity, just multiplied by shear modulus. But we can just eliminate the notion of, eliminate the necessity of knowing or using shear modulus here to make it a little bit more kinematic by saying it's just slip times area. What that allows us to do is something pretty cool. Here I'm showing the Cascadia subduction zone. And in the left-hand figure, there's a map of where, how much slip is occurring. I think that should be not meters, but millimeters per year, constrained from geodetic data. And so the up dip part of it is fairly locked. The down dip part of it is fairly creeping. The up dip part is locked more in two locations or so. Hypothetically, if we have that and we run it for some number of years, we will have accumulated a certain amount of moment on it. When an earthquake occurs, here it's a synthetic magnitude 9, that moment will essentially be drained out of the fault system. It will be taken away from it. And so what we can do is we can take the image that's on the left, take the slip on that, subtract out the slip from from what's in the middle from that earthquake, and we then generate a post-event slip or moment deficit field. And that's what's shown on the right here. In this case, a large magnitude 9 earthquake just occurred in kind of the northern half of the subduction zone. And so what that means is we've essentially drained out some of the moment there, and we still have moment to the south that is yet to be released. And this is interesting because it suggests a pattern or a system here. We can continually allow earthquake cycle processes, be it plate tectonic or forcing of some other type, to continually load a fault system and accumulate moment. And we can allow earthquakes themselves to subtract moment out by slipping on the fault. And this is something we can track over geometrically complex fault systems. This is interesting because it's a quantity that we can track that requires essentially very little, if any, knowledge of the mechanics of what's going on a fault. And it might be something that helps push us to understand whether or not, hey, does this fault have more moment? Does it have a lot of moment that's been stored and is ready to be released? Or kind of has it kind of run out of moment for a while? It also helps us to localize where more moment might be accumulating in a way that's history dependent, which is something we definitely want. We can bring similar logic to the timing of earthquakes. And that's what this figure shows here. We have 4 panels. The top shows kind of a really naive interpretation of what the probability of an earthquake in time might look like if you only considered tectonic loading. So we imagine a case where we're just kind of driving some tectonic plates by some mechanism, known or unknown, and they're driven for some reason at some steady rate. They don't change in time. In that case, if the plates have some region, if the fault interface has some region that is coupled, the probability of an earthquake there might be naively interpreted as just kind of growing linearly in time. You just grow until you have an earthquake. Okay, that's one thing we can do, but we want to do a little better. And people have, of course, recognized this. Following a large earthquake, things tend not to stay the same. Empirically, we know that there's an enhanced error of earthquake occurrence called some people consider this an aftershock, ephemeral aftershock region that you can get rid of by declustering earthquake catalogs. Regardless of how we consider it, we know that there's a period of enhanced seismicity. One of the things that's been done in the past, and we can certainly consider, is what happens when you combine these two. So if we look at the row second from the bottom here, we combine this tectonic loading. We have this gradual increase in probability of an earthquake. Then we have an earthquake for some reason that's imposed kind of at will here. And then we have enhanced seismicity due to the Omori effect afterwards. That Omori effect eventually asymptotes to 0, and then we recover the tectonic loading response. That's pretty good, and that's interesting, but we can do better. If we think back to the previous slide, we introduced this idea that we could track moment or geometric moment. And if we do that, we might want to do one more thing to this problem. We might want to take the tectonic loading part, the Omori response, and a geometric moment response and put them together. So the bottom panel shows that. We have a gradual increase before an earthquake. We have an earthquake. We have a rapid Omori response following the earthquake. But we also respect the fact that we've kind of drained some of the moment out of the system. And so instead of returning to the pre-steady state kind of value or rate that it would have been, it returns to the same rate, but at a much lower value. So you DC shift the whole system down after you've had a large earthquake. And this reflects the fact that a large earthquake, if it's big enough, could put a whole region into kind of a period of quiescence where you don't have increased seismicity over, say, maybe you do over the 10 years following an earthquake, but you don't in the 10 to 50 years following an earthquake. And you only slowly emerge from that kind of moment deficit, geometric moment deficit in that time. Now, all of these ideas can be put together in an algorithm. And the one that I've developed goes by the acronym SKY, Stochastic Kinematically Informed Earthquake Sequences. And it roughly looks like this. It takes just the core ideas that we've had and just arranges them in a sequence. Now, roughly, if there's a certain probability, at every time step, there's a probability that an earthquake occurs. A probability weight is called T of T. If the earthquake You take that probability weight, you randomly draw, you see if it occurs. If it does, then you create an earthquake. Figure out how big it is, its moment, its slip, all of those things, and you calculate its own worry response. That's fine. If that occurs, that's great. After it occurs, then what we want to do is we want to update this geometric moment that we're tracking everywhere on the fault system. And then the key thing that we want to do is we want to integrate the Omori response, not just from this earthquake, but from all prior earthquakes that have occurred in this sequence. The last thing we need to do with that is we need to update the time probabilities and the spatial probabilities. That is, how has this change in moment updated, and the Omori response, pardon me, how has that changed where we are more likely to have earthquakes in the future and when we are more likely to have earthquakes in the future. And the key to this entire algorithm working is being able to construct probability weight functions. Here are two examples of probability weight functions that we can use in space and time. Spatial one is shown at the top, and it's really simple. It illustrates very clearly the idea that I introduced a couple slides ago, where I showed the Cascadia example with the magnitude 9 on the northern part of it. Essentially, we have some amount of geometric moment accumulation, which is based on the slip deficit velocities that we can measure today, that is accumulating. And then from that, we subtract out the history of earthquakes that have occurred. That's the second term here. That's the geometric moment release term. So we have a part that accumulates moment, and we have a part that releases moment. The accumulation mark here is modulated by a coefficient called nu here, which is not Poisson's ratio, but it's just some proxy for plastic deformation, some unrecoverable amount of deformation. We can take the same logic and we can use that for the probability in time as well. Here we have the geometric moment part, which is identical to what we've seen before. We have an Omori effect part, which looks just like the classic Omori effect, but the thing that's really important is the last term here. And that last term is the geometric moment release term. That is the part of kind of geometric moment that we've kind of pulled out of the system. That allows that kind of drop down effect following a large earthquake. And you can see that all of these terms, which make sense to us, are essentially wrapped here in hyperbolic tans. Those are just to normalize things in some probability sense. You could use sigmoids, you could use whatever you want to use. Tans are just really easy to control because there's, as you can see with the coefficients, there's a data scaling and then an amplitude scaling here, which is really easy to use. Okay, so I've gone from saying we can measure where we can measure where coupling might be using geodetic data, to we wanted to build numerical models, but it's very, very challenging with complex geometry, to let's think about what we really want. What properties do we really want in these models at mesoscale? And here's how we can construct it. So now what I'm going to do is I'm going to show you output from the SKY's earthquake simulation model. And here's an example from Cascadia. All the examples I show you are going to have 4 panels to them like this. The panel on the far left shows kind of the loading rates. That's the slip deficit velocity that's taken from geodetic data today, and then through a mechanical, through kind of the block models used to interpret where coupling is occurring. The panel that's immediately to the right of that shows the moment accumulation, spatially variable. The panel next to that shows the slip in an earthquake if it does occur. And then the panel next to that shows the total amount of slip that's occurred in time. So at t equals 0, the first step in this simulation, we have nothing. We have ongoing coupling, ongoing slip deficit, but there isn't enough moment for an earthquake to occur yet, so nothing happens. Finally, after some...
It's Chris, I'm sorry to interrupt. Can you push that hide button on the little screen share, the recording at the bottom of your screen? Because it's covering that one. Yeah, sorry, and then go back into, thanks a lot.
No, thanks. It's good to have a Zoom expert on these things. I've only been doing this for 4 years. I'll learn it eventually. So here we see that after 400 or so time steps, there's the first earthquake. It's a magnitude 6, which is relatively small. it doesn't rupture much area. Probably a magnitude 6 is probably 10K by 5K or something like that. As we run forward in time here, we start to generate more earthquakes. After 2,000 or so time steps, there's the first magnitude 7. You can see it's up in the north here. But what's really interesting is in the interim between that first magnitude 6 and the magnitude 7 we have now, you can see both on the moment plot and on the total slip plot this kind of pockmark of other earthquakes that have occurred and have started to fill in some of the space there. Finally, over a very long period of time, after about 8,000 or so time steps, we get the largest earthquake that's generated here. That's a magnitude 8.5. And what I show here is the time step where that earthquake occurs at 8,357 and 1 time step later. And that difference is really cool to look at. So the top one, we can see in the panel that's second from the left, the state of the moment balance, pardon me, not balance, the state of the moment distribution prior to the earthquake. You can see that it's still localized up dip to some extent, but it's not a mirror image of what the slip deficit velocity is. And the reason for that is there's been a whole series of earthquakes that have occurred that have eroded that, and it's reloaded in other ways. Then the earthquake occurs, it's a magnitude 8.5. You can see how much slip occurred there on the panel that's second from the right, and the total slip on the right. What's really interesting is the next panel, is the next row, the lower row. Here, the slip deficit velocity is the same, but the panel that shows the moment distribution, which is the second from the left, you can see how that larger earthquake drained a huge amount of moment from the down dip part of this subduction zone. The earthquake that's shown in the panel next to it is just the same as the earthquake from before. I'm not saying another earthquake occurs at this time step. It's just the last earthquake that happened to occur. So you can see this interaction in space really nicely here, how tracking moment, along with this kind of mesoscale motivated statistical model, allows you to generate a lot of things that make a lot of sense. And here's what it looks like in time. This is just one realization. We can run millions and millions of these realizations. The top panel here, and I'm almost done with slides. The top panel here shows the probability in time. The lower panel is kind of a stem plot that shows the magnitude of events that occur in several different ways. The magnitude is encoded in 3 ways here because I really want people to kind of get it. The size of the circle shows the magnitude, the height of the circle shows the magnitude, and the color of the circle shows the magnitude. So what we can see is we start at time 0 over on the left-hand side, and we just kind of slowly increase the probabilities. Eventually, initially we see a couple small earthquakes occur. Those earthquakes occur. They generate a small Omori effect because in this particular case, I have a magnitude dependent Omori effect. They generate a small Omori effect. And in this case, the first couple of earthquakes do not generate large sequences of follow-on earthquakes. The loading continues, more earthquakes start to pop up. Then at roughly time step 4,000, there's one large earthquake. It's probably a magnitude 7, 8 or something like that. It generates an aftershock sequence following it that includes something that's very Both's law-like, maximum aftershock magnitude of about magnitude 7, and a decay in time. This earthquake was large enough that the probabilities actually dropped so low, there was enough moment drained out of the system that the probability gets close to 0. I don't allow the probability to ever go to 0 in this model, but it gets close to 0 for a couple thousand time steps. Then we see the emergence from that kind of moment, from the kind of reloading of the fault system, and an earthquake sequence starts again. We start to see slow buildup of earthquakes. They all have Omori sequences after them. Any one of these earthquakes could trigger a larger earthquake or a sequence of earthquakes. But in this case, that doesn't happen until there's a large one. There's maybe a foreshock sequence there. There's a large about magnitude 7, 8 again at time step 16,000 or so. And you can see that triggers an aftershock sequence as well. The probabilities don't get quite as low until the next earthquake. The sequence goes on and on and on. In this example, which is just one model realization, we can run hundreds of thousands or millions of these if we want to on any fault system geometry we want. It gives us quasi-periodic occurrence of large events, which may or may not be interesting. In some of these, there may or may not be foreshock sequences. In all of these, the fault zone is effectively mosaicked by a sequence of earthquakes in space. So large earthquakes happen, and then aftershocks tend to occur kind of in the regions around that, or not, pardon me, let me be more specific, tend to occur not in the region where the main shock itself occurred, which is an interesting facet of this model. It doesn't mean it can't occur in the region where the main shock itself occurred. It's just less probable because of the current parameterization. And this sequence goes on, and you can find sequences that look like this, that look very different. There are all sorts of possibilities here. And I'm really excited about this because we can run these types of statistical models now on fault systems that have extreme geometric complexity. We can look at the distances, the distance interactions between these things, and we can track quantities that we care about. Pardon me. We can track quantities that have extreme power in terms of modulating the whole system, but don't require us to know everything about the whole system, which may be an extremely effective path forward for some period of time. So this is what the earthquake sequence looks like. I'm just going to end with a few thoughts. This is the earthquake sequence model. It's called SKIES again. Geometric moment is the powerful tool that we use to kind of link ideas in space and time here. It's a generative model, so you can run it fairly easily. It's consistent with a large number of mesoscale observations. It can be tuned to a large degree. It works great with complicated fault systems. And it could be a tool that helps us to do present day ensemble and kinematically informed earthquake forecasting if people choose to pursue that, because we can generate just not one sequence of earthquakes, but many, many sequences that are consistent with a large number of things that we think we know. Now, the last thing I'll comment on is, as interesting as the earthquake sequence generation is, it relies critically on the idea that we know something about how the faults are being loaded. And so that gets us back to where we started at the very beginning of this talk, which is the imaging of nominally interseismic behavior of the earthquake cycle. So nowadays, we can do large-scale imaging. Shannon Graham's work took us to global scale at some resolution. In places like Japan now, we have 10 million daily position estimates. We have incredible SAR data. A lot of it's produced at the University of Leeds. The NISAR mission is about to launch, well, possibly launch in a couple of years. There are methods out there that allow us to do time-dependent imaging. Fukuda in 2008 wrote a beautiful paper about how you can use particle filters for this. And the thing that I'm most excited about that we've implemented is we no longer have to do kind of single fault models. We can put in a huge number of very high resolution structures today, because numerically we have H matrix and eigenvector compression techniques, and these are all implemented in kind of the software that we develop. And so for the Nankai example that I showed you, the Nankai subduction zone itself, which is just one fault surface here, but that subduction zone itself is resolved down to about, with kind of a triangle mesh size of about 1 kilometer by 1 kilometer. That's of course interpolated from seismic data, but that's extraordinarily high resolution, which is interesting, not in the sense that it gives us necessarily the true fidelity of what's there, but it allows us to simulate things down to very small magnitudes in terms of the earthquakes that can come out of the skies simulations. So that's what I wanted to talk about today. I started with a set of things that we've done for a long time. I then told you about a journey into kind of the numerics of boundary elements and some of the extreme challenges there. A little bit of philosophy on whether or not we need force and how we can think, perhaps, I don't want to say thermodynamically, but we can bring thermodynamics logic about abstracting our understanding to this problem, and then how we can use that type of abstraction to try and build earthquake sequence simulators that do not rely on us having the ability to solve the numerics accurately, which we may not have today. And we can, with the SKYS algorithm, we can, under a certain set of circumstances, generate absolutely astounding earthquake sequence models. So that's what I wanted to talk about today, and I'm happy to take questions. I'm going to try to close the slides gently now.
Wonderful. I'll invite everyone to unmute, turn on your camera if you'd like to, and join me in thanking Brendan for a really fabulous talk. Really, really interesting. Thank you very much.